Okay, maybe if you agree, we can start now.
Yeah.
So, good morning or good afternoon, depending where you are, and welcome to our Koopman operator theory seminar. So today our speaker is Yueheng Lan. I hope I pronounced it well. So before we start, let me know that this talk will be recorded. We'll post it to our YouTube Koopman operator theory forum channel. Uh, so the title of the talk is Koopman operators and applications in nonlinear dynamics. A few words about our speaker. Solan is a professor in the School of Physics at Beijing University of Posts and Telecommunications. He earned his PhD from Georgia Institute of Technology and held postdoctoral positions at the University of North Carolina at Chapel Hill and the University of California, Santa Barbara. His research focuses on complex systems, especially high-dimensional nonlinear systems, with applications in neuroscience, AI, fluid dynamics, and complex networks. He has published more than 100 papers and serves on the editorial boards of communications in theoretical physics and modern mathematical physics. So, Lan, the floor is yours. Please take it away.
Okay. Thank you. Thank you for the invitation and introduction. I'm very glad to be invited to give this talk. And I'm also very glad to know there is such a seminar series existing. So today I'll talk about the Koopman operator theory and its applications. So the title is a little large, but I will do my best to present it clearly. And if you have any questions during my talk, please interrupt. Okay, let me see. Okay. So I view this Koopman operator mainly from a linearization point of view. So I'll talk about the linear and nonlinear dynamics and how to linearize in general. The Koopman operator, I'll give the definition and also its computation. We will present two applications. One is in symbolic dynamics. We'll use Koopman operator, use its eigenfunction to do the symbolic partition. And the second is to check the synchronization transition in chromatal dynamics on a network. Okay. First, so now I think we are in a world of complexity. So the first picture on the top left, you will see a brook in mountains. There are torrents in the brook. Actually, the turbulence in the torrents remains the last classical problem in classical mechanics. And the second one is the starting flying in the sky of Britain, and it will make all different kinds of shapes. It will do all kinds of things. Actually, it's a living system. And at the bottom, on the left, it's a very, very simplified picture of the inside of a cell. You can see two lipid membrane on the top, and on the top you will see a lot of receptors. The signal will pass through these receptors, and through a series of complex chemical reactions, the signal will propagate into the nucleus and do reactions. So this process is very, very complex, and probably of the same complexity is the internet universe. Here, I think each point probably consists of one or hundreds of computers, and they connect to form a big net covering the whole globe. So all these complex systems we are very interested in because they are closely connected to our social and society. So there is no universally accepted definition of complex systems, but we can always characterize some of the properties. The first two is from the structure and dynamical point of view. They have a structure, hierarchical structure. many agents interconnected in a complex manner, resulting in a multi-scale, highly heterogeneous system. And their components will interact to, to form an emergent dynamics, which is not reducible to the individual dynamics because they exist in the interaction between agents. So as a result, the system seems to be able to learn from the environment to show some adaptability to the environment. So the evolution of living creatures is a typical example of this. The system is kind of robust, but also flexible in order to learn from the environment, to change their structure or dynamics to adapt to the environment. So this is a marvelous feature and also difficult part of the complex systems. And of course, because of the complexity, there are also a lot of uncertainties existing in the relation, in the parameter, in even the agents of the complex system. So as long as their mainframe is maintained, their dynamics and function could be maintained. So how to study these complex systems is an open problem. So we achieved a lot in the study of nonlinear dynamics and statistical mechanics. For example, in nonlinear dynamics, we can check the important set. For example, the compact invariant set like equilibrium, periodic orbit, tori, invariant tori, and check their stability, check the bifurcation. And also, if the system is too complex, we may apply a statistical point of view, for example, the statistical mechanics, to check not only one point, but ensemble of points. So we can use ensemble theory to describe the dynamics, to describe the state of the system. So in which the phase transition is apparently one important aspect of the dynamics. So we can study the phase transition with a lot of tools, for example, renormalization group. But when facing complex systems, also many problems arise. For example, the most famous one is the curse of dimension. The complex system living in a very, very high dimensional phase space. So they contain a lot of interacting agents. And through these interactions, many different spatial temporal chaos emerge. So we cannot just do simple averaging or simple decomposition to decompose or to average the system into simpler ones. We have to consider all these hierarchical structures and many, many dynamic modes all together to form a complete and whole picture. So usually we cannot start from a rigorous first principle description because the system is too complex. We usually use some phenomenological theory to describe the system. So which involves simplification. So whether this simplification is correct or not is subject to question. Also, there exist many uncertainties in data parameters, which also brings kind of ignorance or perplexity to the study. Okay, for complex, then do we really have a way to approach this system? So we can check some simple examples. Even though we have a lot of components, we can solve the linear equation quite easily. For example, here we give a ordinary differential equation. So the linear ordinary differential equation, x dot equals ax. Here, x is a state vector which is n-dimensional, and A is n times n constant matrix. For this system, the n can be really large or infinite. But for linear system, it's always possible to separate the solutions into independent modes. For example, we can set xt equals e to the lambda t times v. So the time dependence is very simple. It's just an exponential dependence. When we substitute this form into the original equation, we can get an eigenvalue equation, AV equals lambda V. So as long as V and lambda satisfy this eigenvalue equation, then the above form xt equals E times lambda t times V is a solution of this system. So because the eigenvalue equation probably has n different solutions, n lambda and n v's, so we can have n different solutions to the linear equation. A general solution is just the linear superposition of these special solutions. So this is really nice. But can we apply this to nonlinear system? Generally, no, because in nonlinear system, we don't have this linear superposition principle. So what shall we do? So one simple idea is the linearization. We can always try to linearize the nonlinear system into a linear one by a map AX to map the solution in X space into the orbit in Y space. In Y space, probably is linear. And of course, the map should be reversible. We can always use the inverse map A minus 1 to map the orbit in Y space to orbit in X space. If we can do this, then the system is linearizable, and then we can use the theory from the linear system to do the calculation. But unfortunately, this calculation can only be done locally by Hartmann theorem or Poincaré-Segal theorem. So if the system, so we can linearize around some equilibrium if it's hyperbolic or satisfy some non-resonance conditions. For global linearization, it's always hard. The system should have some kind of properties, for example, symmetrical properties, or the nonlinearity is very weak. Otherwise, it's really hard. But yeah, we approved. So me and Professor Mesic proved in the basin of attraction of a fixed point periodic orbit, then we can always linearize the system in a whole basin of attraction. But if it's not attractive, the point is not an attractive fixed point, it's a saddle, then generally we can only do it in the neighborhood. So here we give two examples. The first one is a 1D nonlinear equation x dot equals x minus x to the cube. Through the transformation to y, we see it's a linear equation in y space. But it's only valid for x in the interval -1 to 1. So we can go a little more complex to a 2D system, z1, z2, and the following transformation can also linearize the system into linear one. Please note that the transformation contains a meromorphic term. It's not totally analytic. Yeah, because the z square actually is a resonance term in the second equation. So, so for simple nonlinear systems, we can always use this kind of linear nonlinear transformation to linearize it. But the problem is that for general nonlinear system, it's really hard to do. So for general system, what can we do? So one consideration is the actually is the energy landscape. So because there is so here we show an example of van der Pol equation. So here is the energy landscape. So in the bottom of the energy landscape, you can see the red curve, the red circle. It's not a circle, a red closed curve. So it's a periodic orbit. So I think away from the periodic orbit, the potential kind of increases. So if you have this kind of energy landscape, you know the solution will kind of approach the bottom, but also it will circulate. So because of the circulation, the equilibrium statistical physics does not apply. Yeah. And also in high dimensional system, there's also, I mean, nonlinear system, there's also a simpler one. A simple one is the gradient flow, which has a gradient, which has a potential function, and the dynamics just flow opposite to the gradient direction. Then the trajectory is very simple. It's just along the gradient and to the bottom of the potential. The Hamiltonian system is a very physics one. Uh, the the trajectory is usually perpendicular to the gradient of the Hamiltonian. In general system, actually the orbit is kind of combination of the gradient and the perpendicular direction. Is a combination. For general system, so it's not gradient flow, it's not Hamiltonian dynamics, but there exists a Morse theorem. It says the system can be decomposed into the attractor-repeller pair, and the whole dynamics can be viewed as a juxtaposition of these pairs. So if we view the attractor or repeller as a point, then it becomes a gradient-like system. It's not a gradient system, but it's gradient-like. There always exists some kind of Lyapunov function which decreases along the connecting orbit. So then we proved if the system is attractive, has a basin of attraction, then it can be linearized. So if we combine these two, then for general system, if we treat the attractor properly, then probably we can build up the energy landscape. Actually, this has already been done by quite a few people. For example, Professor Wang Jin, he used the invariant measure to build the energy landscape, and Professor Ao Pin decomposed the dynamics into a kind of rotational part and a gradient-like part. So there are also other ways. For example, the famous one is the Fredlin-Wentzel quasi-potential. But for general nonlinear system, actually, there does not exist a universal way to construct the energy landscape. But the energy landscape is connected to the linearization. Okay, so another point of view is we switch our point of view from individual trajectories to kind of ensemble trajectories. This is a holistic point of view. For example, for Brownian trajectories showing on the left figure, you can see there are three different trajectories which looks very complex. I think this is probably from the original plot of the pollen suspended on some water surface. So each trajectory looks very complicated, so it's hard to describe. But if you put a spoon or a handful of particles on the surface of water, we can check the density, the evolution of the density. Then it looks very simple. It's just a swelling Gaussian distribution. So this means sometimes if we check the ensemble of trajectories, then probably things get easier. So this then introduces the statistical treatment of dynamical systems. We can evolve the density, which is governed actually by the Perron-Frobenius operator. So it is very analogous to the Schurian picture in quantum mechanics. And we can also check the evolution of observables, the state function in phase space. So this is done by Koopman operator in analogy with the Heisenberg picture in quantum mechanics. So Koopman operator, I think everybody here know its definition. If we have a map and a function, the function is usually called observable. The Koopman operator then acting on the function, get a new function whose value at x is equal to the value at next point of the original function. So it has a lot of advantages. For example, it changes a linear system into a linear one. because the operator, the Koopman operator is a linear operator. Although it's infinite dimensional, then it's linear. So it's totally linear. It contains all the information of the original system. It's totally equivalent to the original system. So in numerical calculation, we can use different modes or points to represent, to approximate the Koopman operator. So the resolution is subject to our choice. So because it's a linear operator, we can approximate with a linear matrix. So the eigenvalue and the eigenfunction contains a lot of information, which is not easy to extract from the nonlinear dynamics itself. So here we show a non-trivial example of the eigenfunction of the Koopman operator. So here there is A. This A is the linearization transformation. So we showed a few slides before. So if we apply the Koopman operator into this kind of linear transformation, so this is the definition of the Koopman operator for a fixed t. And the phi xt actually is the solution of the equation, original equation. So the second equality is from the linearized system. So y is A is just y, is in a linearized space. The Koopman operator, the application, the action of the Koopman operator becomes a matrix, in a linear space. So if we can linearize this A by matrix V into a diagonal matrix lambda, then we can get the second equality here becomes this equation, because we apply V minus 1 on both sides of this equation. So if we set K equals V minus 1 times A, then we can have the following equations. So UTX on this K is equal to this. This is the definition Koopman operator. And this one actually is the above equation. So it's this equation. So if we check each component from here, if we check each component of K, because K is a vector function, it has n components. If we check each component of this K, then it's an eigenfunction of UT because this lambda is diagonal. So to go from here to here, we insert V minus 1 here. So if you have any question, please just ask. So here we see the linearization equation is related to the eigenfunction of the Koopman operator. So in this sense, Koopman operator probably plays some role of linearization and in a more general way. Okay. So here, if we try to calculate the eigenfunction of the Koopman operator in practice, we have different ways. For example, we can just weigh some function, just average the value of some function along the orbit. And when n goes to infinity, we get an eigenfunction of the Koopman operator with eigenvalue 1. If we put some weight before the function value, then we can get a different eigenfunction with eigenvalue with a different eigenvalue. So you can check according to the definition of Koopman operator, the validity of these two statements. Here is just an example to implement what's said just now. So for the standard map with the periodic boundary conditions, so this is a chaotic map at this parameter value. If we, for example, choose the epsilon value as 1, so we choose the observable function as sine 6 pi x sine 4 pi y. Why we choose sine? Because it has a periodic boundary condition. So we choose periodic functions. So we can use a lattice 100 times 100 lattice and evolve each point on this lattice for 1,000 times. and then do the average just mentioned, do this kind of average, along the orbit. And then we mark the value of the averaged function at the initial point. So then we get the picture here. So for this kind of average, there is a simple observation. If 2 points are on the same orbit, then the average should be the same when n goes to infinity. When the orbits are very close, the two orbits are very close, the average on the orbit are also very close. So here we can see different colors. You can see this kind of circle, big circular one, and you can also see this kind of web. You can also see this kind of individual islands. They actually represent different dynamics. For example, in the center of this circle, there is a periodic orb, there is a fixed point. Here in the center of these two, there is a period 2 fixed point, then period 3, and period 5, period 4. So you have all these kind of different periodic orbits. So around these periodic orbits, you can see some kind of island. The island consists of periodic orbits and also quasi-periodic orbits. And here you can also see these green kind of patches. Actually, they mainly consist of chaotic orbits. So different types of solutions are marked with different colors here. So the total dynamics is quite clear from this representation. But unfortunately, this kind of representation cannot be easily extended to high-dimensional system. But the calculation with Koopman operator can do it. So I think probably, yeah. So this is another way to get the eigenfunction of the Koopman operator. We just choose a basis function and represent it in discrete form. Here, x, y, the columns of x, y represent different kind of basis functions. So you may notice they have a different argument. Here is from x0 to xn minus 1. Here for y, it's from x1 to xn. So we can use according to the definition of Koopman operator, when we apply u, the finite representation of Koopman operator, into x, you get y. So this is the definition of the Koopman operator in finite dimensional approximation. So through the pseudo-inverse, you apply the pseudo-inverse to get ut. So you can get ut from this pseudo-inverse. And then as long as you get ut, you can calculate its eigenvalue and eigenfunction. So here is the calculation on a 100 times 100 lattice. So it's a very regular lattice. You can get a lot of eigenfunctions. Here we show 4 of them. So they capture some interesting features of the original dynamics. We can also do it on irregular dynamics, irregular points. For example, we scatter 100 points along the vertical line in the middle, and then evolve each point for 100 times. Then we get kind of 100,000 points. It's irregularly scattered on the kind of this square. And then we just use this point to represent the functions, different functions, then do the calculation. We can also get eigenfunctions. So here we show 4 of them. They also capture some characteristics of the original map. So the important point is that, so for this irregular point, we can very easily to obtain for high dimensional system just from the evolution of a typical point. Yeah, but if you use regular lattice size there, then there would be too many points. It's infeasible to do it in practice. Okay, so this is just a simple calculation of the eigenfunction. It can partition the phase space into different characteristic regions. In general, the spectra of the Koopman operator can be decomposed into the discrete one and the continuous one. The discrete one, also called atomic one, the eigenfunction usually has some kind of finite weight, but for the continuous one, the eigenfunction, of course, has a zero weight. Yeah. So usually, if you build models, then you can view the deterministic one contribute kind of to a deterministic part, and the regular one, the continuous part, contribute. We just model it as a stochastic process. So all these can be found in Igor's paper. So now I just talk about some applications to symbolic dynamics. First, yeah, symbolic dynamics is a very important tool in the study of nonlinear dynamics. So in a phase space, you can carefully partition into different regions and represent each region with a symbol. So if you check the dynamics, the orbit will kind of travel among these patches. So if you check more carefully, for example, I check its one-step future, then you have to partition each patch into smaller ones. And so for example, a point here means now it's in zero patch. And then after one step, it remains in zero patch. But for a point here, next step, it will go to the two patch. So this is this kind of, so each point can travel among these patches. So you can use a long sequence to record the trajectory. So below is a simple plot of the function logistic map. And for logistic map, you can partition the phase space 0, 1 into two parts by the middle point 1.5, 0.5. So to the left of the 0.5 is 0, to the right is 1. And a trajectory will map just travel around. So you can use a long sequence to record this trajectory. So, but the important thing is, if you do further partition, you find this small interval. We kind of here we label it in 0, 0, because here currently it stays 0, and the next point is still 0. Here is 0 currently, and the next step it will go to 1. So for each trajectory, it has a label, and for each finite label, it corresponds to an interval. For example, for the point here, so it's a fixed point. So it has a unique label 0, 0, 0 to the infinity, 0, 0, 0. For the trajectory here is 1, 1, 1, 1, 1. So also to the infinity. To a periodic orbit here is 1, 0, 1, 0, 1, 0 all the time. Yeah. So each sequence corresponds to one unique trajectory, each infinite sequence. If the sequence is finite, then it corresponds to a finite interval. The longer the sequence, the smaller the interval. So we can build one-to-one correspondence between the points and the infinite sequences. So the dynamics is just a shift of the sequence. So this is called symbolic dynamics. It's a very good topological description of the nonlinear dynamics. So can we do it in general? This is the problem. So actually, this has been done, I think, like in 1980s and 1990s a lot, but now it's not so popular because it's really hard and people are caught in some places. Now, actually, we can use the eigenfunction of the Koopman operator to do the partition. Here is the in one dimension also for the logistic map. We use, of course, finite dimensional approximation with m equals 8 eigenfunctions, not eigenfunction, basis functions. You can see one eigenfunction looks like the blue curve here. And the dots here represent the partition, the main partition. The first one is at the x equals 0.5. The second one is these two. So we can see for the basis, the eigenfunction derived from m equals 8 can capture the main one quite accurately, but the sub-level is not, the points are not very well captured. But for m equals 16, all these points are quite well captured. So maybe just now it's too simple. Then we go to the second, a two-dimensional map. The famous along map is also a chaotic map for a equals 0.3 and b equals 1.4. So we can see the eigenfunctions, the partition point also lies at the extremum of the eigenfunctions. See here show a lot of partition points. Yeah, and actually we can continue to higher dimensional dynamical system, for example, to Diophant oscillators. So it has a drive, a periodic drive. So we can choose a Poincare section as t equals 0, 2 pi, 4 pi as the Poincare section. Then it becomes a map. So for this map, we can apply the same method to partition the phase space into different parts. So here we also show a 3D map. 3D map is also a chaotic map. This is the strange attractor. We can also apply the same strategy to partition it into two parts. So it seems that it's not, there's no kind of absolute obstacle to apply the Koopman approach to the partition of the phase space to obtain the symbolic dynamics, to obtain the symbolic partition. So the second example is associated with the Kuromoto model. So which is described by describes a set of oscillators. We just use the phase and we'll ignore the amplitude of the oscillator. So the operator, each operator has a kind of intrinsic frequency. Here is omega I. I denotes the label of the operator, and they interact. And the Aij is the adjacency matrix, so the operator sits on a web. The K is the interaction strength. Usually, the omega I is chosen from some distribution, for example, from the Gaussian distribution. And we can construct all the parameters to describe the whole, the collective dynamics by put this phi into unit circle on the complex plane and then just sum over all these points, the average these points. So here we give some qualitative picture of the dynamics. If K is small, then every oscillator just goes with their own frequency. So here is the theta t diagram. So the slope of each curve is its intrinsic frequency. So they all go their own way. Then the total, so here you can see the oscillators scatter around the unit circle. When we increase K, then some of them will synchronize. So they will go with the same pace. So the slope, they have the same slope. But other oscillators, or they still do their own way. When K is big enough, then all oscillators synchronize. They go always so together. So we can use the R to characterize this kind of transition. When K is small, R and saturate at some large K value, which means the total synchronization. So this is the distribution we usually extract. Here is the Gaussian distribution of the natural frequency, the intrinsic frequency. So, for example, we put 10 oscillators into, for example, scale-free random network. And the frequency can be chosen regularly, like here, and also it can be chosen kind of irregularly from -1 to 1 randomly. Yeah. Here, for example, we choose the frequency regularly. So when K equals 0, the average frequency is the intrinsic frequency. But when K is not equal to 0, then the neighboring frequencies will approach each other. And at some point, the average frequency becomes equal. This is the synchronization point. So the synchronization continues as k increases, and finally, when k is bigger enough, then all the points have the same average frequency. The average frequency is defined as the kind of a total rotation angle divided by the total time. So for each oscillator. So how to treat this with Koopman operator? We can use the time series from all these oscillators to construct the eigenfunction of the Koopman operator, as stated above previously, and we can check the dot product of normalized the eigenfunction between neighboring strength, coupling strength. You see Kn minus 1 Kn is neighboring coupling. We check their dot product as normalized by their length. So we can define a total correlation by add all these correlations at individual oscillators and then divided by n. N is the number of oscillators. So here we plot. So here we have two figures. We plot the average frequency, how average frequency evolves with the coupling strength, and also how the just now the correlation coefficient evolve with the increase of coupling strength. We can see the correlation function is almost 1, except at some instant it dips quickly and then recovers quickly. At the tip of the dip, it just corresponds to the synchronization points. So this is for the regular frequency, initial frequency. This is for the random initial frequency. So we can see the tip of the dip points to the synchronization. See? Yeah. So why is this? Because usually our k is very close. For example, kn and the kn minus 1 just differs by 0.01. So it's very close. So the eigenfunction changes a little bit, very little, when you from one k to another k. So their dot product is almost equal 1. Yeah, but when you approach a synchronization, the eigenfunction changes quickly because the dynamics change qualitatively at the synchronization point. So then you can see a dip because they become different very quickly. So you can see this kind of dip. So with this method, we can check kind of here is just an example. So we can always use this to check more subtle bifurcations. For example, there is a subtle bifurcation here. There is a dip here, very shallow one, but it points somewhere. There is no synchronization, direct synchronization, but actually there is a generalized synchronization. The frequency of some guys, they just the ratio of two frequencies become integer. Then there's a generalized synchronization. So you can see this kind of dip. So it's a more subtle one. So we hope in general nonlinear system, this can also detect the synchronization, phase transition, or other types of bifurcations. So with this, we come to the end. So to the summary, first we can use Koopman operator to provide a way to linearize, in some sense, the nonlinear system. Okay, so I think this is a little strange. Yeah, second one, actually the eigenmode could be constructed through numerical calculation, which can reveal the most important dynamics. Yeah, the third one, actually, this is related to our application. It can be used to construct symbolic dynamics, reveal bifurcations, and also identify qualitatively different dynamics in high-dimensional nonlinear systems. Of course, we also have a lot of possible future research direction and also challenges. So although there are many ways to do the calculation, actually there is no reliable and efficient way to compute a spectral property for a complex system with limited data or limited computing power. The second is how to select important modes from a huge number of modes, because we use a lot of points to approximate the Koopman operator. It has a high dimensional the matrix. So there are a lot of eigen modes. So which ones are important is a problem. So in order to find the important ones, we have to know its physical significance. So there are so many of them. So it's hard, really hard to find the physical significance for each of them. But can we find the important ones? So this is still a problem. So although, of course, we can do it according to our intuition or some physical interpretation, but in general, we don't have a universal way to do it. Then finally, it's related to the modeling. Can we use these important modes to build reliable models for complex system to kind of model what we are interested? So I think now I just end here. Thank you. Thanks a lot.
Thank you, Lan, for your nice talk. I think we have time for some questions. So, are there any questions? Okay, maybe I have one question. So maybe this is like more general, and maybe this could be a question in this generalization and the challenges. So basically, do you maybe see a path toward automated discovery of optimal observables? So I think it's like one of the main problems in, especially in data-driven settings. So when you collect some data and you're trying to build a Koopman model, the choice of observables is always a problem. So in all applications
Yes.
that I faced with, this was the main issue. So do you see some perspective in future how to automate this procedure, how to find this observables in a good observables or optimal observables in an automated fashion?
Yeah, I think this is a really interesting question, also related to these questions. And also, I think this is a research topic, very important one. And yeah, I tried all different kinds of methods. For example, I choose different bases, Fourier basis, polynomial basis, and also Gaussian basis to do the calculation. They all have different effect. And also, I think now usually I just choose the natural basis. We just use the given data and use the Hankel matrix to do the calculation. But when you do the calculation, probably you do a SVD to get the main observable from the SVD first, and then use the basis extracted by the SVD as your functional basis to do the calculation afterwards. I think usually this kind of calculation is okay. Yeah. But when the data is scarce, not so many data, then you have to construct your own basis according to your prior knowledge. Yeah, for example, you already know somebody, probably other people say something are very important, then probably you choose this important quantity to be the basis. Then the calculation would be more efficient and more reliable. So I think currently there's no universal way to do this. This is a very good research topic. Yeah, I think this question is very relevant.
Yeah, thank you. Are there further questions, maybe? Okay, if there is no more questions, let's thank to our speaker. Thank you, Juan, for your nice talk, and see you on the next Koopman Operator Theory seminar.
Okay, see you guys. Thanks a lot for attending this talk. Yeah, bye.
Bye bye.
Mhm.